idea. So let's say that you have an input y equal to wx. This is like the fundamental equation on which the entire machine learning happens. So now let's look at like the dimensionality of this kind of equation and why I think it is flawed. So let's say that your x is like the input and it is like of length L and it's having a dimension of d. And let's say that your weight matrix is like a standard weight matrix which is of d cross d. So now look at like what happens in case you multiply these two equations. So the weight matrix has a dimension of d by d, and then x has a dimension of uh, l cross d. So you do wx transpose, so you get d cross l. And finally, like whatever, these two d's cancel and your output is essentially y, which is d cross l. So in this case, as you can see, like whenever your network sees an input x, the size of the output actually grows linearly with the size of the input. And you can see that this is like really a very stupid thing, because definitely like when you see like whether you see anything from like when you close your eyes and see only a part of the world, or whether you open your eyes and you see the whole world, or whether you look at like whether you look at a video for a long time, or whether you look at an image, like the memory or like the activations in your brain don't explode as a function of time. So the point is that your brain is inherently recurrent in nature, and it should not be parallel like a transformer. So the biggest blunder which we have made in attention is as follows. So let's say you have like this L sequence, and what you do is like for each of these tokens, like you're computing like a additional vector which projects this token into like a separate into like separate it is projecting like each of these tokens into like a separate key, query and value. So you did this. So if your if your sequence is of length L, then the number of key matrices you will have will be L. And then so total like you will have, so so your total keys will have size L cross D, and similarly Q and V, they will have L cross D size, and the total memory you will occupy will be 3 L cross D. And this is just too much memory. And this is like a problem which cannot be, which is like really stupid, because like if you have like a if you have like a sequence of any length, then the size of like the your memory bank is actually growing linearly with the size of the input. And in the brain, like obviously your brain doesn't have this memory bank to shuffle off this information to, and this is like really wrong. So from a memory perspective, this is like the biggest blunder attention has made. And from compute perspective, when you do like the standard attention mechanism, which is q into k transpose times v, this turns out to be quadratic, right? But like if you perform some sort of kv caching, you can get that time down to linear. And that's a very interesting hack which the community has come up with. But if you look at the memory, the key point is that the number of key, query and value which you need to compute still scales linearly with the sequence length, which is like very stupid, right? Because as you know, like your brain does not have that information. Turns out I talked to like a lot of people in the community about this, and they don't care because they can just keep paying money for the hardware. But I think this is the key point why we are not able to do inference. And this is also another point, like if you are like processing like 5 or 10 or 100 frames in a video, you have to store like the separate feature representation for each of the frames in a memory bank to be able to operate on it. And if you can solve this issue, if you can reduce this memory from order of L down to order of 1, then we are talking. Because if we build something which takes like this constant amount of memory, it starts resembling more of our brain, and then it really works well. So what is like one way which we could do about it? What's like one way in which we could go about it? So the point is like we already have something like a RNN, which looks so in which like if you have like a input sequence, you look at like every word one at a time, right? And that is really good because the memory here doesn't blow up. So memory here is still constant, and that's like the size of the hidden state which your network has. Whereas like the memory in transformer is really big, and that's like order of L. So the point, and here like the memory I think is order of 1. So the key point is that how do you build, but here like in RNN you face like the vanishing gradient problem, and in case of transformer you don't have those issues, but you pay the cost in terms of memory. So there should be like a fundamental fix to this problem, and for that like I would like to make a detour and discuss about neural fields. So turns out there is a concept in machine learning which is known as neural fields. And what neural fields do is that they have like a neural network, and the weight of this neural network does not the size of this neural network does not depend on the size of the input. So if you have an image of let's say 10 by 10, or if you have an image of 100 by 100, or you have an image of 1000 by 1000, technically this same size neural network can learn to fit on this image. And what you can do is like you can actually, so let's say this input grid has like a coordinate x1 y1, and then it similarly has a coordinate x and yn. So technically like you can query this neural networks x1 y1 and get like the output at that location as the output. So here like instead of like, so it gives you like the ability to process each location independently. So you can process this location, you can process this location, this location, and this location, and then you don't need to actually use up a lot of memory, right? Because the key point is that in this case what happens is that if you have like 5 locations, you can just query this neural network with 5 forward passes and still pay the cost of keeping that neural network in memory, like whose weights, and its memory never increases the weights, because you don't end up like computing these hidden activations at all. So turns out like there is a fundamental fix for this problem which is known as the glom paper, and my own work on asynchronous perception machines which was published in neurips, and I will talk more about that in a later video. But this was like trying to make it, this is like trying to call out a fundamentally impossible problem, in which like the size of intermediate activations scales linearly with the size of the input. And it like this is like a way, this is like a call that we should be actually fixing that problem. And until we fix it, like we are not gonna get something which is resembling our brain, because our brains occupy finite memories, and we can't afford to keep paying the cost of occupying additional memory. Okay, so see you in the next video.